Hi, my name is Sun. It is my great honor to present our paper, Temporal Multiresolution Graph Neural Networks for Epidemic Predictions in the Healthcare AI and COVID-19 workshop at ICML 2022. Mathematical modeling and simulation of epidemic dynamics play an essential role in understanding and addressing the spreading of infectious disease in the real world. It is important to acquire knowledge from the social networks or traffic networks via graph-based mathematical methods to make prediction on how quick infectious disease spread over the community. Our problem can be defined as follows. Given a graph G, where V is the set of nodes and E is the set of edges, depending on the application we might have, V can represent counties or individual people. E can represent the neighboring information between two counties or the interaction between two people. For example, in this figure, we have the geographical map of Hungary with 20 counties and its graph representations. Each node is associated with a time series signal that can represent either the number of infected cases in a country or the health status of a person. Each edge is associated with a time series signal that can represent either the amount of traffic between the two counties or the indicator if two people interacted during a given time. In general, given a graph dynamics where GT indicates the graph at time t, we need to predict the future signals. For example, the number of infected cases in a county in a number of weeks. Our contribution can be summarized as follows. First, we propose the use of multi-resolution graph neural networks to capture micro to macro or local to global information of a pandemic. Secondly, we apply an attention mechanism to select the right resolutions that predict the current state or progress of the pandemic. We combine them into a temporal architectures incorporating time series information to make future prediction about the pandemic given historical data. Finally, our experiments show competitive results on two temporal datasets of COVID-19 and chickenpox in several European countries. The core of our model is the multi-resolution graph network, MGN, that was originally proposed in our previous paper, multi-resolution equivariant graph variational autoencoder. MGN applies higher order message passing neural networks to learn to cozen or cluster the graph on each resolution and build a hierarchy of latents in a data-driven manner. The top figure shows the aspirin molecular graph, its three cluster partitions, and the corresponding cozen graph. The bottom figures show its hierarchy of three resolutions. Here is an example of a temporal two-resolution simulation of an interaction network of 4 people. The red color denotes the person gets infected by some virus, and the green color denotes otherwise. In time step 1, only one person gets infected, and the quotient representations contains 2 clusters with label 3 and 1. Gradually, the virus spreads from one to others, and in step 3, when everyone gets infected, the quotient representation contains a single cluster with label 4. It is necessary to use multi-resolution in modeling a pandemic because a pandemic always starts localized and increases the number of cases over time as more and more people get exposed and infected. Therefore, we need to capture both local, micro, and global macro informations. This diagram describes our temporal architectures. To detect the current state of a pandemic, we apply the attention mechanism over multiple resolutions to select one resolution at that time to be fed further into a long short-term memory LSTM backbone. The LSTM backbone can capture the long-range temporal dependencies in time series and robustly predict the spreading dynamics of the virus. As a result, our model outperforms several other state-of-the-art temporal GNNs by 11% in predicting the chickenpox epidemic in Hungary over 40 weeks long forecasting. Furthermore, we support our claim by strong numerical results on COVID-19 pandemic predictions in several European countries. For example, our model outperforms all other statistics, time series, and temporal GNN baseline in 3, 7, and 14-day prediction in England. Finally, we release our implementation and dataset on GitHub. Thank you very much for your attention.